My name's Jason Hammons. I lead the technical team in VAST. I've been at VAST for probably about 5 years, and we've done I think a lot of interesting things that I'm going to share with you today, both in cloud and in life sciences. Our main goal when we started this company was we felt like the only reason customers decided to tier storage, especially with hard drives, was because of cost. So one of our sole aims was to give customers everything they need, but mainly to drive cost out of the system. And we did a lot of work over the years that I'll talk about here in a moment, but I think some of our best work in the early days was designing a system that was built for cloud. So obviously, we needed to bring a lot of design points into this new product that are suitable for HPC and NVIDIA. But we also need to bring a lot of cloud control and cloud security and all these other management things that you need. And we actually got quite lucky that we started on that probably 2 years before the ChatGPT event. And since that time, we've also been very fortunate to be a part of a lot of these neoclouds globally. And now I'm proud to say today we have quite a large global footprint and exposure to a large number of NVIDIA GPUs and a number of really good successful projects. The great thing about it is it gives a lot of choice, I think, to a lot of customers. So we do actually have a very good reach within life sciences. We actually started working on a lot of HPC projects on the back of COVID, and we were fortunate enough to be very successful in life sciences and HPC. So marrying those two together, it's been quite a game changer for our business, and we feel quite lucky. There'll be maybe some things in the news coming soon that I can't talk about, but we're very, very fortunate at this time. And one of the other key principles that we built this product on was a lot of the existing storage systems that came before us really were designed with what's called a shared nothing type of architecture. The base case for that is that these architectures are tightly coupled server node architectures that generate a lot of internode traffic, typically between a 30 to 50% of a tax that you pay when you design these systems. And in some cases, they may look cheap, they may look great, they work at a reasonable scale. When you start scaling out to a large capacity and large bandwidth and large parallelism, which is obviously required for HPC and NVIDIA, that's when they start to break. So we took an approach of basically decoupling state from logic, and that has served us very well. It allows us to scale performance and capacity independently, and it gives customers a lot of choice and a lot of flexibility as they scale out. It also gives them a lot of capability around real-time delivery of applications that don't have to worry about that internal tax that gets imposed on internal traffic. We can give single client performance to all of the NVMe devices using a lot of massively parallel techniques that we've engineered into the product. And it helps us become very resilient at scale and also equally affordable at scale because our customers benefit from a global deduplication and compression database. And even in life sciences, we've seen, I think, a lot of really fantastic returns on that that doesn't impact performance, and it gives customers, of course, lower cost. So that's the basis for, I think, the early work that we did. But then probably about 2 years ago, we decided to take another great step forward and try to take advantage of this single unified platform that's highly efficient, highly performant. Could we build some native services into this platform that run on containerized out-of-band containerized out-of-band engines that can access all of this metadata, but don't impact client performance? All the HPC scientists, they still get all the performance they want. But what if we could add all these new things like serverless triggers and functions, kind of a Lambda type functionality into the product? What if we could add an internal vector database? What if we could add an internal data warehouse? And the customers don't necessarily have to pay for that. It just comes with a product. And what we've really kind of come to at this point is, yes, we've done very well with storage and we do all these great things with multi-protocol access, but now we're starting to give customers more choice around using their own event broker inside the product, using their own database, using their own vector database for embedding search with NVIDIA. And the knock-on effect of that is it's produced some really interesting design points that customers really just didn't have choice with previously. Up to this point, our partnership with NVIDIA has mostly been based on achieving this NVIDIA Cloud Partner certification that is very difficult to get. It took us a couple of years to kind of get everything through the program, but now that we have that certification and that reference base, we feel like we're very, very solid with high performance storage, and of course, that's up to the spec that you would see with the latest Vera Rubin GPUs, and that's great. But what if we could also provide a data lake that gives you the same levels of performance, and suddenly you have additional tooling that is native inside the product where you can accelerate data processing and feed those GPUs faster and start engaging in using LLMs to do smarter and AI-driven ETL instead of using older data engineering tools that were built 10, 15 years ago. And so this introduced a lot of interesting things. From our perspective, I'm going to give you a few examples of how we do this a bit later. It allows customers to take advantage of all of the enterprise capabilities that we've built into the platform to govern everything from model training to inference to building an agentic platform. And so at the data services layer, there's a lot of, I'm not going to call it boring stuff, but a lot of sort of run-of-the-mill enterprise services that people take for granted. Things like multi-tenancy and having hard multi-tenant capabilities at the data layer. Things like having unified permissions across a single namespace. This can be quite key because as customers now are starting to build out with things like vector database, we have a customer right now that we're in a project with that used a vector database that I can't name. It's a very good one, but they ended up, because it struggled to scale, they ended up building 50 vector database instances to make it work. So with their agentic use case, when their agents go to do searches, they have to search all of these endpoints. With VAST, you have the ability to scale that out on one single namespace at very large scale, and it gives you the added benefit of having much faster, seamless semantic search across everything. It's a really, really cool capability. I'll give you a couple of examples later on how we do it. Additionally, some of the things that are starting to come up now, once we solve the performance problem, once we accelerate ETL and we accelerate data processing, then there's some other problems that arise that customers are now interested in, and that is having a global distribution network that behaves as one. So we've introduced some data sovereignty and inferencing at the edge capabilities that allow us to provide customers with a single representation of a multi-site cloud capability where their engineers only see one directory, they point their code at one directory, but behind the scenes, the infrastructure team has several sites that they can load balance that with, and they maintain operational control over that. And of course, the data scientists don't have to worry about that. They don't have to make a decision. They don't have to constantly fine-tune their code and run it in certain locations. And that makes it very, very easy to establish a policy-based access that is unified across the entire system, super easy to manage. If someone changes teams, you can immediately turn them off across the entire business. And that's been quite beneficial. It's also quite beneficial for doing inferencing at the edge. So we've enabled a KV cache capability that allows you to do deep context or deep memory context to basically save a huge amount on recomputing all of that data as these models go reproduce things. And we can link those KV cache extensions from multiple sites and still give that single representation to a data scientist or, of course, an end user. Last year we did, it's notable, right around this time, there was a nice talk at GTC. It's still on NVIDIA On Demand, but CoreWeave, who's a very big customer of ours, did a very nice presentation on how this global namespace functionality works. They did it with Jane Street, which is a hedge fund. What's interesting about it is Jane Street has a very, very big deployment of GPU clusters, but they needed that burst capability into a neo cloud that's going to give them GPUs at about 50% of the cost that they're going to buy in the hyperscalers and available 100% of the time. And it gave them the seamless capability of giving that single view to their quants who could then take snapshots of their data and just restart their models on those snapshots and have a very, very easy cloud burst experience into a NeoCloud. The multi-tenant piece, I won't go into detail about, but I will say that one thing that makes us very different, a lot of people talk about multi-tenancy, we're actually delivering it in these NeoClouds at very, very large scale. We do it into the tens of thousands of tenants, and we do it at a higher standard of security than most other providers, and we've had quite a lot of success with it. And our enterprise customers really, really enjoy it because it gives them the ability to manage their keys, retain control over their security, and ultimately retain control over all of their metadata while they burst into these NeoClouds. When we talk about the data processing piece, there's actually some interesting stories that I want to share with you in terms of how we're applying this and what they kind of look like. We have some public references that you can see on our website in this section. This particular one I can't talk too much about, unfortunately, but I can talk about how we do it in general. In this case, with MRI imaging. With most MRI imaging, ML pipelines that have been built up to this point, you do get some interesting things with metadata tagging that you can do. What makes VAST different is, as these images are imported into our pipeline, we can automatically, as they land, we can create alerts that then trigger an operation or a function to do something with that information, okay? In this case, the information or the doing or the function is essentially triggering the NVIDIA's embedding services using their NIMS catalog and their models to go in and summarize everything that it finds in that image. And of course, we build out a number of prompts to give that agent the unique insight into what it should be looking for in that image. This is actually quite easy. Our engineers we've built a lot of these pipelines ourselves. We don't have, our developers aren't really that advanced, but they know how to use Cursor, and they can do a lot of very interesting things with this. And what they end up doing is basically being able to take that data and populate that into our database so it becomes immediately searchable at the point to which you ingest these images. And typically, as you ingest an image, probably takes us about, 6 to 8 seconds to be able to integrate with those embedding services, trigger those models to summarize what's in the image, and then we vectorize that automatically with our pipelines, and then that vectorized data becomes immediately searchable. Okay, and then this customer in particular, they have a very simple front-end search, enterprise search that they've built. Now you have enterprise semantic search, and you have it across all of your imaging data. Another interesting thing that we decided to do with NVIDIA actually is they asked us to start building connectors for all these other endpoints, SharePoint, Office 365, G Drive. So many customers have data locked away in these places and they don't know what they have. And they asked us, could you just build a tool that makes it easy to automatically go index what we have elsewhere and then ingest it on demand. And we just tell the tool what we want to import into the system. Why is that interesting? Well, it basically means that if we can then index all of these external sources and actually use that to, this is going to be a little bit complicated, but at the data ingest point, if we can create an alert that uses a Kafka trigger to kick off our ETL process, then suddenly as you ingest this data from SharePoint, call it, we can automatically classify that data using NVIDIA's models and the deep semantic search that they're doing on these files, depending on what you want to see. Now, in this particular example, I call it data classification as a service. It's just something that we built for a couple of customers who basically told us, we have so much data, but we have no idea what we have. So we built a very simple pipeline. All of this is completely automated. As the file is dropped into VAST, it essentially takes a summary of the file, which is very lightweight in terms of the amount of GPU that it uses. It vectorizes that summary, and then within about 6 seconds, you get a very good deep classification in terms of what's in that file. It goes well beyond what typical metadata tags will give you, right? And this doesn't use a lot of GPU. This is really lightweight, simple. You can, there's tons of Nematron models you can choose from that'll do this. And then the best part about it is we have additional triggers and functions in these pipelines that you can define through a simple UI interface. If you decide that you have a highly classified document that needs deep vectorization, you want to spend a little bit more GPU power to do that, you can actually trigger that as well. So it gives you a lot of flexibility, and you can do a lot of different things for simple things like data classification, which there's an entire product ecosystem that was built for this. Now you can do it with VAST and NVIDIA in a single stack with no other product, which is really, really cool. So the last slide I'll end on, this probably is a snapshot of all of the things that we're working on. All of this is done in partnership with NVIDIA. We've been working with NVIDIA engineering for a couple of years now, building out not just reference architectures for AI factories, which is very important, but also blueprints for things like document RAG, video search and summarization, and now we're starting to do some things with genomics and sequencing. And what that means is, as was stated earlier, you get a blueprint that is predictable, it's been tested, and you can go deploy it and you know what you're going to get. The additional benefit I think that you get both with you doing this with VAST and NVIDIA is I think you get a better support experience as well. So following an AI factory build with using NCP, we were working with a pharmaceutical that I can't name who came to us and said, hey, we want to build an AI factory, but we want it to follow NCP. And we were like, yeah, but that's for cloud providers. They're like, we know, but we know it works. And we know that you guys have built a lot of them. So we want something that's predictable and reliable, and it's going to give us the same experience that we have on-prem. And one day we may go burst to a neocloud. We want the same experience in both places. And I think that's really key. Is we have, I think, a lot of we have a lot of references behind us now in terms of what we've been able to prove with delivering, highly available GPU infrastructure. And then also you get all these additional capabilities with accelerating ETL and doing all these cool things with an agentic platform that's built natively into the product. So that's it for me. Thank you very much.